Hello, I'm Jack Jackson, and today we're going to be talking about complex numbers. We'll define what a complex number is, and we'll see how that grows out of earlier numbers a little bit, but mainly we're going to be focused on doing some arithmetic with complex numbers, learning how to do things like add, subtract, multiply, and divide them. So we're going to start with a review of some algebraic properties of rational numbers that we developed for natural numbers and then expanded to rational numbers, and these will ultimately be true for actually real numbers and complex numbers as well, including some exponent properties. We're going to then define the complex number system and see how we can graph complex numbers. Then we're going to talk about how we can do some operations with complex numbers. We'll start with addition and subtraction. We'll move on to multiplication, conjugates, division, powers of I, and we'll end with talking about the norm, or sometimes called the modulus. So let's review something we did quite a bit earlier in the course. We start with the most basic kind of numbers, the natural numbers, 1, 2, 3, 4, etc. And if we put two of those groups together, then we've got the basic operation of addition if we're counting how many's in the total. If we repeatedly add the same thing over and over again, that's called multiplication, at least when we're dealing with natural numbers. If we repeatedly do that, then that leads us to exponents. So repeatedly multiply the same thing over and over again. That leads us to the idea of an exponent. And these things make sense in the natural numbers. But if we want to undo these operations, we have to expand the number system. So if we want to undo addition, we need subtraction, and that leads us to the integers. So we get some negative numbers that way. If we want to undo multiplication, we need to divide, and that leads us to quotients or fractions, which leads us to the rational number system. And if we want to undo exponents, that leads us to the real number system, and then further than that, actually to the complex number system. Okay, so we undo exponents by roots or radicals or fraction exponents. Of course, ultimately you can think of everything really as add, multiply, or exponents, because subtraction is adding the additive inverse or the opposite. Multiplication is multiplying by the multiplicative inverse or the reciprocal. And exponents roots can be thought of as just fraction exponents. Okay, so in expanding our number system or in solving some simple equations, we need to go out ultimately to the complex number system. Now we develop certain properties of algebraic properties of numbers, and these were properties we developed first mostly for natural numbers in operations, and then expanded this in some cases, particularly in the inverse case, for bigger number systems. Okay, and ultimately these are going to hold for any complex number. So if you have any complex number A, B, and C, first of all, it's closed, so we'll see a little bit later on as we define addition and multiplication that when you add two complex numbers, you'll get a complex number. When you multiply two complex numbers, you'll get a complex number. Addition is associative, so if you add A plus B first and then add C, that's the same as adding B and C first and adding that to A. And same way for multiplication. It's also commutative. A plus B is the same as B plus A, and A times B is the same as B times A. So both addition and multiplication are commutative. And they both have an identity element, which is what we call 0 for the additive identity. So if you take A and add 0 to it, you get A back again. A retains its identity. The identity element for multiplication is 1. A times 1 is A. If you have an identity, then you can talk about inverses. And there's always an additive inverse. So if you take a number A, there's always an opposite number that you can add to A and get 0. And this is still going to be true in the complex number system. And except for 0, every number is going to have essentially a reciprocal, a multiplicative inverse, something you can multiply it and get the multiplicative identity, which is 1. And then we also have this 0 multiplication property, that anything times 0 is equal to 0. And in fact, if you have any two things multiplied together to get 0, then one of the two things has to be 0. And then finally, we have a property that combines addition and multiplication. The other properties are either just for addition or just for multiplication. But we have the distributive property here that says A times parentheses B plus C is the same as A times B plus A times C. And again, all these properties, even though they worked earlier, we've expanded our number system in such a way that these properties will still work for all complex numbers. Then we also developed, particularly in this unit, we've developed this a lot, this idea of exponents. And so here's some properties of exponents. Okay, and these are going to make sense for us. In particular, we have, just some of these. I won't go over all of them right now, but if you multiply two things, the same base, you keep the base and add the exponents. When we divide, we end up subtracting the exponents. That produces negative exponents, which leads to properties 6, 7, and 8, these flipping properties that the negative exponents have. And property 3 says if you have a base to a power, and then a power on that, then you just multiply the two powers, keeping the same base. That leads us to the idea of fraction exponents, okay, and so forth, and you can see some of these other possibilities here. And so, of course, when we have fraction exponents, another way to write that is with the radical. And so here we have some properties of radicals which really come from the properties of exponents. And the last couple here have to do with actually non-real numbers, and that's part of what we're going to be talking about today. So, where do complex numbers first sort of show up? Well, you can take a really simple equation, x squared equals -1. It's a pretty simple little equation, and it turns out that's not going to have any kind of a real number solution. If you take any positive number and square it, you get a positive. If you take 0 square, you get 0. If you take a negative and square, you get a positive. There's nothing in the real number system that you can square and get any kind of a negative. So if you have x squared equals a negative number, there's no solution inside the real number system. But of course, we'd like there to be a solution to that. That's a real simple little equation. We'd like to be able to undo squaring. So to do that, of course, we have to expand our number system. It's a pretty easy expansion, really. So whatever this number is, one of the solutions should be -1 to the 1/2 power, or in other words, the principal square root of -1. That should be one of our answers to this. And so we, since this is not a real number, we need a new name for it. We call this number I. And so I is this imaginary unit. So I is defined to be this number, which is -1 to the 1/2, or the principal square root of -1, so that when you square I, you get -1. So I is what we call our imaginary unit, and it is a solution to x squared equals -1. The other solution is the opposite of I. So I, or -I, those two things are the two solutions to this, I, or the opposite of I. So this shows up when you're taking roots of a negative. So it turns out if you take the nth root of -1, if n is an odd number, that always turns out to be -1. If n is an even number, that turns out to be something that's not real. It's a complex number, but it's not real. Specifically, if n is 2, the square root, then the square root of -1 is I. If we're talking about the 4th or 6th or 8th or 12th or 54th power of -1, those turn out to be neither real nor just pure imaginary. They do turn out to be complex numbers. As we'll see, that's in the a plus bi form. You get a non-zero a and b. We're not going to talk about that in this course. All we're going to say is, hey, it's not a real number. So we can define a couple of sets of numbers based with this number I. So the imaginary numbers are the numbers of the form b times I, where b is a real number that's not 0, and I, again, is this principal square root of -1. So imaginary numbers would be numbers like 3i, pi I, square root of 2 times I, -4 times I, or just I. Not 0i, because 0 times anything is 0, which is a real number. So the imaginary numbers, we want them to be completely separate from the real numbers. These are called the pure imaginary numbers, or just imaginary numbers. Now, I've seen some books, which I think incorrectly, call any complex number an imaginary number if it's got an I in it. But in fact, what I think is the more proper definition is that it's only a pure imaginary number if it's b times I. So we have some complex numbers that are neither imaginary nor real. And complex numbers then, written by our indicated by this blackboard boldface C there, or the open face C. That is numbers of the form a plus bi, where a and b are real numbers, including possibility of 0 now, because if a and b are both 0, then you get 0, which is a complex number. And if you get b is 0, but then a could be anything, we get all the real numbers, and we see that they're a subset of the complex numbers. And if you let a be 0 and b not 0, you get all the numbers that are imaginary numbers. So the imaginary numbers are complex numbers as well, subset there. And we also have other complex numbers like 3 plus 2i, 4 minus 7i, etc. So we see that the complex number system is this number system here, and it includes many of the other number systems that we've talked about. So notice that it includes the real numbers and the imaginary numbers, okay? Which the real numbers, of course, then include the irrational numbers, the rational numbers, the integers, the whole numbers, and the natural numbers. So you have a nice little expanding sets here. You know, the set of natural numbers are the most basic numbers. They're a subset of the whole numbers. The whole numbers then are a subset of the integers. Those are all subsets of the rationals, which are all subsets of the reals, and all those are subsets of the complex number system. Okay? So it turns out that complex numbers are actually closed under addition, subtraction, multiplication, division, powers, and roots, except that division by 0 or 0 to the n for a non-positive n are undefined. And we can represent complex numbers by points in a plane. Okay, we'll get to that in a second. So if we let z be a complex number that's in the form a plus bi, where a and b are real numbers, okay, the real part of z, denoted by Re of z, or Re of a plus bi, is the a. So you might think the imaginary part is the bi, but actually the imaginary part is just the b. So the imaginary part of a plus bi is just the b. So notice that both the real part and the imaginary part are actually real numbers. Now here we get to graphing these, and of course you know every point in a number line corresponds to a real number. We can actually find complex numbers as points in a plane. So we have a horizontal axis, kind of like the x-axis. That's going to be the real axis, and the vertical axis then is the imaginary axis. So numbers on the real axis are just, the real axis is the real number line, and numbers on that are actually the real numbers. So, and then we just plot points like this one here that you see over here in the second quadrant. That's the point. It'd be the ordered pair negative 4, 6, and so we plotted at that point, but that represents negative 4 plus 6i. So of course if the b part, or y-coordinate, second coordinate, is 0, then you're on the x-axis, or the real axis, and you get a real number. So for example, this dot here on the horizontal axis is 3 plus 0i, which is just 3. That's a real number. The imaginary numbers are the numbers on the vertical axis, except remember 0 is also on the vertical axis, and it's a real number that's not imaginary. But the other ones on the vertical axis are exactly the imaginary numbers. So this one here on the vertical axis is at the point 0, 5. That's 0 plus 5i, or just 5i. I have one here in the first quadrant, that is 3 plus 3i. Sorry, that should say 2 plus 3i. Okay, 2 plus 3i. Okay, and so forth, and you could graph any complex number in the plane. So again, I've already said this, but the set of complex numbers is closed under addition, subtraction, multiplication, division, powers, roots. Not all these things we're going to do in this class, but there are a couple exceptions. 0 to the 0 is undefined. In fact, 0 to any negative power is also undefined. 0 divided by 0 is undefined. In fact, a divided by 0 is undefined for any a. So if you have 0 to a non-positive power, or anything dividing by 0, that's undefined, which of course we've always seen that it's undefined. Now you can also think of a plus bi, which is a single complex number. You can also think of that as the sum of a real number a and imaginary number bi. And so you can split that apart. So that truly means that plus in the middle truly means addition in the complex numbers. So a plus bi is, a plus 0i, which is just a, plus 0 plus bi, which is just bi. And so we add those together. Because the basic rules of algebra are just generalized rules of arithmetic of natural numbers, and we want them to be valid in the set of complex numbers, operations with complex numbers are basically the same as operations on binomials. So in other words, you can treat the I just like it's an x and work with it just like you would a polynomial, except that we make use of the fact that I squared is -1. So, with that in mind, we can add complex numbers. So a plus bi plus c plus di, we can think of those as 4 separate pieces. A plus a bi plus a c plus di. We want addition to be both commutative and associative, so we can reorder and regroup at will since it's all addition. So we group the real parts, the a plus c, together, and then the bi and the di, we put those together. And then we can factor out, with using the distributive property, factor the I out of the second one, and we get a plus c plus b plus d times I. So that will actually give us our definition of addition. So a plus bi plus c plus di is defined to be a plus c plus b plus di. So if we have this, the real part of the sum is just the sum of the real parts, and the imaginary part of the sum is the sum of the imaginary parts. So let's look at an example, pretty easy to do. 3 plus 2i plus 4 plus 6i is 3 plus 4 plus 2 plus 6i. So that's, in other words, add the 3 and the 4, you get 7, and add the 2 and the 6 and get 8. So it's 7 plus 8i. Pretty easy to do. Similarly, subtraction, basically you distribute the negative and think of it as 4 parts, a plus bi minus c minus di, or plus a negative plus the opposite of c plus the opposite of di. Reorder and put them together, and you get a minus c plus b minus di, like you'd think it would be, right? So when you do 3 minus 4i minus 5 plus 7i, for the real part you get 3 minus 5, which is -2, and -4 plus 7i, you add the -4 and the 7 to get -4 and -7 to get -11 for the imaginary part. So it's -2 minus 11i. I'm sure you could do these in your head. They're pretty easy to do. Now remember, we have the distributive property. Okay, so if we have a real number times a plus bi, we can multiply that real number times each part, and so that's a times c plus b times ci. If we have something a little more complicated like a plus bi times c plus di, remember the distributive property leads to our FOIL shortcut, first times first, the outer two times each other, the inner two times each other, and last times last. And that's just the distributive property. Okay, the same thing that leads us to how we would multiply two two-digit numbers. So we have a times c, that's the f. The o would be the a times the di, so that's ad times I. The I is the bi times the c, so that's bc times I. And the L is b times d, bi times di, which is bd I squared. Now, as often happens whenever you have polynomials like this, binomial times binomial, often the middle terms are like terms and they add up, and that's true here. You get ADI plus BCI is AD plus BC times I. But something happens interesting here that doesn't usually happen in a polynomial. If this I was just an x, you'd have x squared and you really couldn't simplify. But since this I is not a variable, it's actually a constant number, it's a specific number I, we know that I squared is what? Well, that's -1. So that's -1 there, which makes this, that's where this negative comes here on this BD. So the I squared is -1, and so this last part is actually a real part, which adds to the AC, and so those parts combine, and so we end up with just sort of the two terms at the end, AC minus BD for the real part, and AD plus BC for the imaginary part. So let's look at a few examples of these. Okay, so if you have 2 times 5 minus 6i, that's 2 times 5 is 10, and 2 times -6 is -12, so it's 10 minus 12i. If you're going to distribute an I, you can distribute it as well. I times 3 is 3i, I times -4i is -4i squared. I squared is -1, so that changes that from -4 to a positive 4, and I just re-switch the order to get it in a plus bi form. It's 4 plus 3i. The next two we're going to use the FOIL method. And the part C, I've actually written out all the details. D, I've done a little bit more in my head, which is the way I think you're probably going to end up doing it yourself. So 3 times negative 2 is for the F, that's negative 6. The O is 3 times 5i, so that's 15i. The I, the inner part, is negative 4i times negative 2 is positive 8i. And the L is negative 4 times 5 is negative 20, and the I times I is I squared. Now I squared is negative 1, so that becomes plus 20. The 15i plus the 8i add up together, factor the I out, add the coefficients, that comes 23i, and then 20 minus 6 is 14, so you end up with 14 plus 23i. You don't really have to write down all of that much detail. I wanted to do that once so you could make sure you could follow it, but I think the next one is more like what you might actually write down by hand. 2 times 4, so this is 2 minus 3i times 4 plus 7i. 2 times 4 is 8, that's the F. The O is 2 times 7i is 14i. The inner product is negative 3i times 4 is negative 12i. And the last times last is negative 3 times 7 is negative 21i squared. I squared is negative 1, so that makes that plus 21. 21 plus 8 is 29. 14i minus 12i is 2i. And so we can do that. You might even be able to do the whole thing in your head with a little practice. Now what about division? So we've already done multiplication. So let's do a couple of simpler cases first. So if the denominator is a real number, then all we have to do is basically remember dividing by, for example, in this case, dividing by 2 is the same as multiplying by half, so we can use the distributive property to divide the 2 into each part above. So 8 plus 4i is 8 divided by 2 plus 4 divided by 2i. Of course, 8 divided by 2 is just 4, and 4 divided by 2 is 2. So that's 4 plus 2i. Now, if the denominator is a purely imaginary number, then we have a little technique we can do here. We want the no i's in the denominator. So the thing that you can do is just multiply top and bottom by I. Notice in the bottom, that will give us an I square, which is negative 1. So now we just have negative 6 in the bottom, and then it reduces to a problem like the last one we just worked. Notice this is legal to do because the fundamental equivalence property of fractions says these fractions are going to be equal if we multiply the top and bottom by the same thing. Or another way to say this is we're just multiplying by 1 in the form I over I, and I over I still is 1. Anything divided by itself is 1 except for 0 divided by 0. And so this gives us what we want. So if we multiply the bottom by I, then we get 6i squared, which is negative 6. That gives us the desired effect of getting rid of the I in the bottom. Of course, we have to multiply the top by I2, and we use the distributive property to get 3i. And then the 4i times I is 4i squared becomes negative 4, because I squared is negative 1. Now just distribute that negative 6, and we get negative 4 over negative 6 for the real part, which reduces to positive 2/3. And for the imaginary part, we get 3 over negative 6, which reduces to negative 1/2 for the imaginary part. So our final answer is 2/3 minus 1/2 I. Now what if we have something a little more complicated like this? 3 plus 4i divided by 2 minus 5i, or you could think of it in fraction form, 3 plus 4i divided by 2 minus 5i. Well, will our technique of just multiplying the top and bottom by I work? Okay, well, no, that doesn't work. In this case, look what happens. Okay, it does get rid of the I. It does change the I into, if we multiply it by I, it does change the I to an I squared, which becomes negative 1 times the negative 5 is positive 5, but unfortunately, it then multiplies that also the I by the 2, so then you got a 2i, so it just sort of switches where the I is. So that's not a real number, so that's no good. Alright, the next thing you might say is, well, what about just squaring it? Okay, well, that's 2 minus 5i squared is 2 minus 5i times 2 minus 5i. Again, use our FOIL or our definition here. 2 times 2 is 4. The inner product is negative 10i, and the outer product is negative 10i. And the last times last is plus 25i squared. Of course, that's going to give us 4, and negative 25 is negative 21, but unfortunately the middle terms add up instead of canceling out. And so we still get an imaginary part, a non-zero imaginary part, so we had a non-real complex answer, negative 21 minus 20i. So squaring it's not going to work. So remember in general that if we take x plus y squared, we get x squared plus 2xy plus y squared. Can you remember any particular one that whenever you multiply it out, you get rid of that middle term? And hopefully maybe you recall that there's a pattern called the sum and difference pattern, where you take x plus y times x minus y, and you get x squared minus y squared. The f of the FOIL is x times x, which is x squared. The L is y times minus y is negative y squared. The O part is negative xy, and the I part is xy. So you've got the inner product and the outer product cancel each other out and go away altogether. And that's going to be useful for us because the imaginary part is from that inner and outer products. So let's try that out with this. So you have 2 minus 5i. You just do the same thing with the change the sign on the imaginary part, and we get 2 plus 5i. Now if we do our FOIL, we get 2 times 2 is 4. The outer product is 10i, and the inner product is negative 10i, and the last times last is negative 25i squared. So notice that that we have the inner products cancel out, and we have 4 and then plus 25, which is 29, which is a real number. So that's what we need to multiply the top and bottom by in this case, is the 2 plus 5i. So notice this number that we're going to multiply by is called we have a name for it. It's called the complex conjugate, and we indicate that with a line over it. So the complex conjugate of a complex number is of a complex number a plus bi is the number a minus bi. Okay, and notice if you multiply by the conjugate, look what you end up getting. You take a plus bi times the conjugate of a plus bi, that's a plus bi times a minus bi. And notice we get a difference of 2 squares from our sum and difference pattern gives us a difference of 2 squares. It's the first term, a square, and then minus, then the second term, bi, and square it. But of course, bi square is b square, I square is negative 1, which changes the difference to a plus, and so we end up with a square plus b square in the end. So we know if we multiply by the conjugate, all we get is a squared plus b squared, which is a real number. So let's put that into play to define division. A plus bi over c plus di. You multiply top and bottom by c minus di, and the bottom you're going to get c squared plus d squared. And of course then the top you got to do your FOIL thing there and combine, and you can see the details worked out here. In the top you get a times c, you get b times, I'll do the L next, bi times negative di is positive bd. Notice it would be negative bd and then I squared, but I squared makes it positive now. So I squared is negative 1, which multiplies by the other negative 1 makes positive 1. So you get AC plus BD, okay, and then you get BC minus AD for the other part, okay. But then you want to divide both parts by C squared over D squared, and of course then the real part of your quotient, your division problem, is AC plus BD all over C squared plus D squared, and the imaginary part is BC minus AD all over C squared plus D squared. Now rather than trying to just memorize this, just remember that you got to multiply the top and bottom by the conjugate. So we're back to our problem that we were doing a while ago. Let's go ahead and do that. We just want to multiply, actually this may be a different problem. 3 plus 4i divided by 2 minus 5i. We want to multiply the top and bottom by the conjugate, which is 2 plus 5i. It's just the opposite sign on the imaginary part. Keep the same sign on the real part. And at the bottom you're going to get a squared plus b squared, so it's 2 squared plus 5 squared is 4 plus 25. And the top you just got to do your FOIL thing here, the distributive property. 3 times 2 is 6, 3 times 5i is 15i, 4i times 2 is 8i, 4i times 5i is 20i squared. 20i squared is going to be negative 20, plus the 6 is negative 14. 15i plus 8i is 23i. 4 plus 25 in the denominator, that's going to be 29. Distribute the 29, and we get negative 14 29ths plus 23 29ths I. And we see we can convert that into the a plus bi form, which is what we want to do. So we see that we can do this basically all the time. So as long as we're not dividing by 0, we can do any kind of complex add, subtract, multiply, or divide now. Now let's look at some powers of I. Well, let's start with some easy things. Of course, I to the first power is I, and by definition, I squared is negative 1. Well, it should be that I to the 0 power, just like any non-zero number to the 0 power, should be 1, and in fact it is. I cubed better be I times I square. I square is negative 1, so it's negative 1 times I, which is just to be written as minus I, or negative 1I. And so we get those things. I to the 0 is 1, I to the 1 is I square is negative 1, I cubed is negative I. Now it's interesting when we go beyond that. Let's look at I to the 4th. Well, I to the 4th is I squared times I squared, which is negative 1 times negative 1, which is back to positive 1 again. Notice we've cycled right back up to the same thing as I to the 0. That's going to be a very key property, that I to the 4th is back to 1 again. Then you do I to the 5th. Well, that's just I to the 4th times I, so that's 1 times I, which is I. I to the 6th is I to the 4th times I squared, so that's 1 times I squared, which is negative 1. I to the 7th is I to the 4th times I to the 3rd, which is 1 times I to the 3rd, which is negative I. Notice I've got my same things again. So I to the 0 is 1, but so is I to the 4th. And looks, when you get I to the 8th, that's the same thing again, and so is I to the 12th, and I to the 16th. So as long as the power is a multiple of 4, you're back at 1. If the power is 1 bigger than a multiple of 4, like 1, 5, or 9, it's the same as I to the 1st, which is just I. If the power is 2 bigger than a multiple of 4, like 2, 6, 10, 14, 18, 22, etc., those are all going to be the same as I squared, which is negative 1. And if the power is 3 bigger than a multiple of 4, okay, that would be the same as I cubed. Multiples, those numbers would be like 3, 7, 11, 15, 19, 23, etc. for the power. All those are going to be the same as I cubed, which is negative 1. So really all we have to do is see how is basically see what the remainder is when we divide by 4. So notice this out here. I'll work out all the details here, and then we'll just see we can actually do this as a shortcut. 57, if we divide by 4, is 14 remainder 1. So that means 57 could be written as 4 times 14 plus 1. So that means it's I to the 57 is I to the 4 times 14 plus 1, which is I to the 4 times 14 times I to the 1. I to the 4 times 14 is I to the 4th raised to the 14th. I to the 4th is just 1. 1 to the 14th is just 1, and 1 times whatever stays the same there. It's the identity. So ultimately we just get I to the positive 1 power. Well, if you notice, the only thing that really mattered in the end was that we ended with whatever the remainder was on this division by 4, that was the power we ended up with at the end. So we can just sort of cut to the chase and go straight there if we want to. So I to the 57th, just divide by 4, we get a remainder of 1, so that's going to be the same as I to the 1, which is just I. So notice, was it important we divided by 4? Yes. Why? Because I to the 4th is 1. Okay? So that's going to be important. 4 is the smallest positive power that you can bring I to get 1. So it is important. Was it important that this was 14 for the quotient? Not really, because once you got I to the fourth is 1, it doesn't matter what this power is on the outside. 1 to any power is still just 1. So the quotient up here is totally irrelevant. The only thing that matters is this remainder. That's the only power that's remaining at the end. And what are your possible remainders? Okay? Either 0, 1, 2, or 3. So it boils down to just knowing these. So I to any power is either just 1, I, negative 1, or negative I, based on the remainder. Now, if you have some huge power, okay, anything really 3 or 4 or 5 digits, 100 digits, 9 digits like I have here, remember that 100 is a multiple of 4. So if we take 358,258,775 for our power, we can write that as 358,258,700 plus another 75. So split off the number formed by the last 2 digits. Well, however many hundreds you have, that's a multiple of 4. So that part's just going to be 1. So really all that matters is the last 2 digits. So I to whatever this huge power is, the only thing that really matters is the last 2 digits. So that's the same as just I to the 75th. And then divide that by 4, I get 18 remainder 3. The only thing that really matters there is the remainder. So I to the 75th is I to the third. And of course I to the third is negative I. And there we go. So we can do I to any power. Okay, one final concept is the norm or modulus of a complex number. So if you have a number a plus bi, notice that the distance from the origin on the complex plane is what we call the norm or modulus. And we use what looks like absolute value there. In fact, it is absolute value if it's a real number, because the distance from 0 on a number line is given by the absolute value. Well, the distance from 0 in the complex plane is also given by essentially absolute value. We don't call it that. We call it the norm or modulus. Okay? And so what would that be? Well, the horizontal distance from 0 is the absolute value of the real part, and the vertical distance is the absolute value of the b part. And we can use the Pythagorean theorem to find the distance there in blue, which is the hypotenuse of this right triangle that you see. So absolute value of a squared is the same as a squared. Absolute value of b squared is the same as b squared. And of course you need the square root of that. So the norm or modulus is just a squared plus b squared, and then take the square root of the whole thing. So it just follows from the Pythagorean theorem. Alright, so we've pretty much finished all the basic things. Now let's practice a little bit. So here's some examples of these things. So here I have 2 complex numbers, and I want you to add, subtract, multiply, and divide them. I have a pretty large power of I there, and then a norm of a particular complex number, sort of one of each kind of problem that we've talked about. And once you go ahead and do these, come back and check your answer here in just a minute, see if you followed everything we did on this. Press pause now. Okay, so here we go. The first one, we're just adding the real parts and adding the imaginary parts. 3 plus 4i plus 5 minus 7i. You just add the 3 and the 5 to get 8. You add the 4 and the negative 7 to get negative 3 for the coefficient of the I, the imaginary part. Subtraction, we need to distribute the negative before we add. So that becomes a negative 5 plus the 3 is negative 2. That becomes a positive 7 plus 4 is 11. So you get negative 2 plus 11i. Multiplication, just remember FOIL, and remember the I squared is negative 1. The F part is 3 times 5, which is 15. The O is 3 times negative 7i is negative 21i. The inner product is 4i times 5, which is 20i. The last times last is 4 times negative 7 is negative 28. And then you got I squared. Remember, I squared is negative 1, so that becomes positive 28 plus the 15 is 43. And then for the imaginary, you've got negative 21i plus 20i is negative 1i. So the answer is 43 minus I. When we're dividing, just think of writing it in fraction form. 3 plus 4i over 5 minus 7i. Multiply by the conjugate of the denominator. So multiply the bottom by 5 plus 7i. Then you'll multiply the top by 5 plus 7i. If it had been dividing by 5 plus 7i, you would have multiplied by 5 minus 7i. So you're going to get a sum and difference problem in the bottom, which gives you a difference of two squares, and the I square is going to turn that difference into a sum. And so we're going to get 5 times 5 is 25, 7 times 7 is 49. They're added together to get 74 for the denominator. And in the numerator, of course, you have to multiply by the same thing that you did in the denominator, and of course just use your FOIL, and you can see the details worked out there. This time the numerator is negative 13 plus 41i. Then finally distribute to get it in a plus bi form, so you get negative 13 over 74 plus 41 over 74i. Okay, and now we have D, part D there. It's I to a power. Well, the only thing that matters first of all is the last two digits, so it's just I to the 58th power. Divide 58 by 4, we get a remainder of 2. It's 14 remainder 2, so the remainder 2 is the only thing that matters. So that's I to the second power. Whatever the remainder is, that's the part that matters. And of course I squared then is negative 1. When you have an I to a power, remember it's either going to be 1, negative 1, I, or negative I. Those are the only possibilities. The norm or modulus of 3 plus 4i is just 3 squared plus 4 squared and then square root. So that's 9 plus 16 is 25, and square root of that would be 5. So what should you be able to do now at this point? After doing this and practicing it a little bit, you should be able to, first of all, define what a complex number is. Find the following operations on complex numbers, basic ones: add, subtract, multiply, and divide. You should be able to find the norm or modulus of a complex number, the real and imaginary part, and you should be able to graph a complex number in the complex plane. Okay, and you should be able to compute integer powers of I. We didn't do any negative powers, but remember a negative power is just a reciprocal, so rewrite as a reciprocal, and then multiply by something by an I if needed to get the denominator to a real number. Okay, so that is an overview of complex number operations.